it's a pleasure to look on a lot of faces that are here because they want to come and not because it's a required course. So what I'm going to try to do tonight is to illustrate with demonstrations the evolution of some of our musical instruments. They started out from very humble beginnings, and they have evolved from those beginnings into the presently complicated and expensive shapes that we see today. To begin with, we want to think a little bit about the quality of a sound that we listen to. I have an instrument here which there's a tendency for this microphone to ring. Is there some way to turn it down a little bit? Yes, it'll be very disconcerting if this keeps up. I wouldn't know which microphone is doing it. All right, that sounds, yeah. Does it sound all right out there? Fine. Now here's an instrument which the books generally call a monochord, which would of course mean one string, but this has two strings on it, so I can't really call it a monochord. The scientific catalogs call it a sonometer. Its basic function is to teach students of physics the relationship between the vibration frequency of a string and the mass of the string and its tension and so on. Now, what I want to use it for here is to talk about the quality of a sound. We seem to, for some reason, have grown up with an appreciation of certain kinds of sounds as being pleasant, and the vibration of a string is such a sound. Now, maybe it came from the fact that in the early days of bows and arrows, the twang of a bowstring had a pleasant sound, especially if your aim was good with the arrow. We have become accustomed to string sound as being a pleasant one. Now, there may be some arguments here as to whether this is a pleasant sound, but at least it is illustrative of a string sound. Now, the thing I want to point out here is that this string vibration is actually rather complicated. When I draw the bow across it, I produce a sound which has a certain frequency in cycles per second. Now, I think we all, when I use the term frequency, I guess we all know what we mean or what I mean. But this sound is more complicated actually because it has in it not only this frequency that we hear, but it has in it a frequency twice as great also, which I can demonstrate. For instance, if I touch the string in the center, it immediately sounds an octave higher. And of course, string players know this. This is what they call a harmonic. And when I touch it in the center, then I am producing a frequency which is exactly twice as great. It's very exactly for a string like this. Now, the frequency of the vibration is inversely proportional to the length, to use the physicist's highfalutin language. So if I divide it into thirds, which I can do by touching it a third of the way along, then it sounds an octave and a fifth higher than the lowest mode. I'm going to start using a little bit of technical language, which I'll try to explain as I go along, and if I forget to, which I'm likely to do, you might remind me that I haven't defined it. But this lowest frequency we can call the fundamental, and anytime we have a whole series of possible notes, the lowest one we'll call the fundamental. So I'm explaining that now in case I use the term. So here's the fundamental. Here is the next mode of vibration, and this, in the case of the string, we'll call a second harmonic. It has exactly twice the frequency. Then this one that I get by getting a third of the length is the third harmonic. It has 3 times the frequency. Then here's the fourth harmonic. Here's the fifth, sixth, seventh, eighth, ninth, and that's about as far as I need to go. Now, the important thing is that when I bow a string, all of those are there simultaneously. Although we don't hear them, they all join to form the particular quality of the tone. And I can demonstrate that they are there by bowing the string, getting the tone, and then touching it in the center, and that stops all of the vibrations except the second harmonic. You see, it was there all the time, but you just didn't hear it because it was mixed in with the other sounds. Similarly, if I touch it here, there you hear the third harmonic. Now, maybe you can hear that. Maybe you can hear that in there now that you know what to listen for. But it's there. And similarly, the fourth harmonic is there also. You can hear it there, and so on. So the sound that you're listening to is a mixture. of a lot of frequencies, but they're fairly simply related. They are the fundamental, the second harmonic, which has twice the frequency, the third harmonic, 3 times the frequency, and so on. So this is the characteristic of a musical tone that has some kind of quality to it, rather than just if you listen to what we call a simple tone, which is only one frequency, it is quite a lifeless kind of thing. And our musical tones are made up of complex tones like this that are mixtures of more than one frequency. Now, what we have been listening to is what we can call a harmonic series. There are frequencies which are related, then 1, 2, 3, 4, 5, and so on times the fundamental. And let's listen to it once more. 1, 2, 3, 4, 5, 6. So there are the first 6 tones of what we call a harmonic series. Now, because I'm going to use this later on, I want to go through the odd harmonic series, which will be 1, 3, 5, 7, 9, so that we can sort of fix that in mind, because that's going to pop up later on. So here is 1, 3, 5, 7, 9. So there are the first 5 terms of an odd harmonic series. They go fundamental, octave, and a fifth. If you want to think of them in terms of the musical staff, the harmonic series would be C, C an octave above, G above that, C above that, then E, then G, and then a kind of a flat B flat, and then C again. That's the series a trumpet player is quite familiar with. The odd harmonic series would be given as C, G, E, B flat, D, that sort of thing. So with those in mind, we can go on now. Now, this instrument, of course, has evolved into, or rather the stretched string, not this instrument. I'm going to write a concerto for sonometer sometime, but that's so far in the future. But it's not really a musical instrument yet. But the string, of course, has evolved into a number of different forms of the various members of the string family, ancient and modern. And I'm not a string player, and I'm not going to say anything more about strings. There are other people that are working on them and doing a good job. Now, I am a wind player, and so basically what I'm going to talk about are the wind instruments, but I have to start in with this to lay the groundwork. Now, just as a string can vibrate, an air column can vibrate. Now, this is a piece of brass tubing, but the function of the tubing is simply to contain a column of air. And it's the air that does the vibrating. Anything that I get out of this tube is because of the air inside of the tube vibrating, and not because the tube itself does any vibrating. Now, the tube will vibrate. I can get twangs out of it, but that's not important. That's not what I'm talking about. I can get the air inside of the tube to vibrate, and the way it does so, perhaps some of you, of course, know what a sound wave consists of, and maybe some people don't. If somebody is off in the corner there blowing a horn at me, I get sound waves from it, and the sound wave is a motion of the air back and forth like this. At the frequency of the sound, and if he's sounding, say, tuning A, it's going back and forth 440 times a second. Along with that is a variation in the air pressure above and below the normal atmospheric pressure. So a sound wave is a combination of the motion back and forth and the pressure up and down above atmospheric. So now, if I'm going to produce a vibration in this tube, I can get a vibration in the tube just like I can with a string. And the way it vibrates is, since this tube is open at both ends, the way the air vibrates is in and out of the two ends. So it goes in both ends. It can't go this way. It has to go in opposite direction than the two ends. It goes in at both ends and piles up in the middle and creates a point in the center then where the pressure is high. And then it goes back out the two ends and pulls the air out of the tube somewhat and leaves the point in the center where the pressure is low. So it's going back and forth. And the frequency of that vibration depends on the length of the tube. Now you can barely hear a pitch associated with that. Can you hear? There is a pitch associated with that, and that is the vibration of the air in and out of the ends of the tube. It doesn't last for very long, but it does last long enough for you to get a sort of a pitch. Now, it's also possible for the thing to vibrate with one end closed. And you leave the one end open, and the air goes in and out and piles up against the closed end and vibrates just as it did to the open tube, except that it is now vibrating half as fast. You see the frequency is now down an octave from where it was. And that means that the frequency is half as large. So we can speak of this as an open tube and a closed tube. And they vibrate in this fashion. But they can also vibrate with higher modes also, just like the string can. I have to describe these things in more detail. A string you can see vibrating, but you can't see the air vibrating in these tubes, so you have to be a little more sophisticated about it. Now the physicists have worked out the way the open tube will vibrate and demonstrate that it will vibrate just like the string does, with a fundamental frequency determined by the length of the tube, a frequency twice as great, 3 times as great, 4 times, 5 times, and so on. It has all the harmonics in it, just like the string does. If you close one end, that restricts it. Now it vibrates half as fast at the fundamental, but now it can only vibrate with the odd harmonics in it, 1, 3, 5, 7 that I demonstrated here. Now you can also have a tube vibrating with both ends closed, but that's of no great interest because no sound can get out of it, so you don't know whether it's vibrating or not, so we won't discuss that any further. Now, of course, to get a musical instrument to function, we have to get this vibration to go and to keep it going in some fashion. We have to supply energy to it. We have to excite it in some way. And there are various ways of doing that. I've been doing that here in a kind of a transient way. I get a momentary vibration, but of course what we want in a musical tone is a vibration that keeps on for some length of time. Now, there are 2 main methods of doing this for our musical instruments. One of them utilizes the fact that if I take a stream of air, such as from my lips, and blow it against a sharp edge, it tends to flap across the edge, flutter across the edge, and create a sound. Now, this is the end of a plastic instrument of some kind that I found somewhere. I pulled the end off of it, so it's nothing more than a whistle mouthpiece now, so to speak. It directs a stream of air against an edge. And so it makes that sound that you hear. Well, that's not a very good sound musically, but now if you attach this to a resonant system, by what I mean a resonant system, something which has vibration frequencies of its own, it will generally vibrate at the frequency of the system that it's attached to. Here's a simple musical instrument. I'm not advertising this particular brand, but if I blow a stream of air across the edge here, this is attached now to this volume, which can be set into vibration, just as the tube can be set into vibration, with the air going in and out of the mouth. And the stream of air keeps that vibration going. So this is, I guess a lot of people are familiar with this Coke bottle effect. Very often, if you're out in the open and the wind is blowing at the beach and you open a bottle of Coke, you'll hear that tone as the wind blows across the mouth of the bottle. So here we have a system which has a frequency of its own that's kept into vibration by this particular effect. Now, if we want to make a musical instrument out of this, we can do that. Now, this is an illustration, and I think now is a good time to show the first slide, because what I want to show here is an instrument which uses this effect. We are attaching a tube to this system here, in which we blow a stream of air against this edge. And the vibration in the tube, in this case, it's open here and it's open here. So the vibration consists of a motion of air into this end of the tube and simultaneously in and out of this open part of the tube. The fact that this is on the side and this is on the end makes no difference. It works the same way. So now what happens here is that you blow the stream of air in. Now let's suppose that the sound wave in the tube is at this particular time going in. Well, that sucks the stream in with it, and so the stream moves with the air that's flowing into the tube, and they aid each other then. The air stream flowing into the tube helps the vibration. Similarly, when the air stream turns around and goes out of the mouth, then the air stream from the slit is directed out and helps it again. So in this way, the stream of air maintains the vibration, and it's at the frequency of the tubing. Now, that frequency is determined by the length. I can effectively shorten it by cutting a hole in the side of the tube. If I keep that hole covered, then it's just as though it weren't there. But if I open up the hole, then the tube is shorter by approximately this amount. It actually depends on the size of the hole, but it is shorter, and so the frequency is higher and the pitch goes up. Now, that, I think, is enough of the slide to show us, this is to demonstrate this particular instrument, which this is a very expensive instrument. I think it cost me 25 cents down in one of the souvenir stores in Chinatown. But it demonstrates the way these things can vibrate very nicely, because here is a plug in here with a slit cut in the side of it, so I direct a stream of air against an edge which has been made by shaving in the side of the tube. And when I do that, take that cork out of there first, I get a frequency, which is the vibration, fundamental vibration of this tubing. But now we said that a tube which is open at both ends, which this is, open here and here, will vibrate with, can also vibrate with twice the frequency, and it will if I just blow a little harder. So that's the next mode of vibration. Now it can also vibrate with 3 times the frequency. There's 3 times the frequency. And it will do 4 times. The frequency depends, you see, on how fast that stream is going. So this is we can speak of this as the 4th mode of vibration. I don't know whether I can get 5 or not. Yeah, there's the 5th mode. It's getting pretty loud now, so maybe I better stop there. But this thing, you see, shows the same modes of vibration then as the string. And you recognize this as the same pattern of harmonics that we had for the string. Well, this is not a very musical instrument yet. The number of tones it will play is rather limited. However, as I pointed out, we can open a hole on the side of the tube. I've kept my fingers over the hole so far, but if I open a hole here and then uncover it, the pitch immediately goes up a tone, and so I have the beginnings of a musical scale. All I have to do is to put in enough holes, and I get I can make a scale. Now, all I need to make the diatonic scale are 6 holes, and that plus the whole tube makes a 7-note scale. Now, I have to drop the other shoe, so I will blow a little harder and get up to the octave. So there I finished it off. But these 6 holes, 3 for each hand, is a basic scale and shows up in all the woodwind instruments. They all have these 6 holes somewhere along the line, covered with the 3 fingers in each hand. Now, of course, this allows me to play tunes. Now, of course, we don't want to stop here, but it so happens that this tube, being a cylindrical tube, has the property that the same holes will work up in the next mode of vibration. If I blow a little harder, get part of a scale up there. It doesn't want to work all the way for this instrument for some reason, but I can blow the 3rd mode and go on up further. No, it doesn't work that way. Well, that's far enough, but you see I can cover more than an octave by using first the lowest mode, which we call a low register, and then the next mode, the next register, and so forth. So this thing develops then into a musical instrument of sorts. It's not a very fancy one, but at least it illustrates the basic properties of an instrument. This thing now develops, if we make this a little more elaborate, we get the recorder, which is the same sort of thing. It has a mouthpiece with a slit that we blow through and finger holes and everything. I didn't bring one. I'm not a recorder player. I'm going to be in the position here tonight of bragging about how many instruments I don't know how to play, and it will become perfectly obvious that I don't when I've got through here. But if you elaborate this instrument further and make it in one which you blow across the hole instead of down the instrument, the principle is exactly the same. You're using your lips to form the airstream instead of using the thing that's already built into the instrument, and you blow across instead of down, but there's no difference basically, and so you have a flute. And I also didn't bring a flute. I was never able to play the lowest notes on a flute, and so I wasn't going to demonstrate my lack of ability in that direction. Well, this has developed in other directions, of course, too. If we have simply an air column with the slit mechanism here at one end, we have an organ pipe. We don't have to do anything about tone holes or anything else, because an organ pipe is designed to sound only one note. So it does so, and we have 1,000 of these in an organ, and we can play quite a few different notes. Now, this can be either open at the end, like it is now, and blow this, or it can be closed, in which it sounds roughly an octave lower. Now, any musician will tell me immediately that that's not an octave. And I have to agree that it isn't, because I'm a musician too. And the reason it isn't is that the frequency depends on the length of the tube, but at the open end, the air is vibrating in and out of the end, and it goes a little ways past the end before it washes out into nothing much. And so the tube actually looks like it's about so much longer when it's open. When it's closed, then there's no such effect. So the tube actually looks a little bit longer, and the amount longer depends on how wide it is. Now, this is a fairly wide tube, and so that effect is rather pronounced. On a tube like this, it isn't. Well, of course, the flute has developed into quite a sophisticated instrument, and I really can't say much more about it. I have discovered that flute players think that the lip vibrates when they play the flute. It doesn't. There are a number, in the course of this talk, I will probably step on a few toes in that I will say that things aren't so that some people have believed to be so for some time. And I don't mind in the slightest arguing about it. If you want to argue with me about it, I'm prepared to. Now, the flute is developed in other directions. There's one of about half the size, which plays an octave higher, the piccolo. And there's the bass flute, which is a good deal larger. It's really quite a sizable thing. Plays much lower and so on, but I won't go into that. Because now there's another very fundamental way of exciting vibrations in an air column. Now, this is done by putting a reed on the end of the column. And most of us are somewhat familiar with the clarinet, for example. This is a clarinet. And we have this column here. The fact that this flares at the end is of no acoustical significance as far as I've been able to determine. It might just as well go out here and then stop. But it's customary to build them like this. But this is an air column now, which actually looks closed at this end. This is the big difference between the column, between the air column open at both ends, represented by the flute and the recorder and so on. Now, the clarinet looks like a column which is closed at this end where the reed is. Now, the next slide gives us a sort of a cross-section view of the clarinet. And this is not to scale, of course. It's got to be a lot longer than this. But now we have a vibration of the air in and out of the open end. Now, there's no, this end looks essentially closed. The air piles up against this end and generates then a pressure, a high acoustic pressure. It's alternating above and below the surrounding atmospheric pressure. Now, there's the so-called reed is attached to this end, and there's a very small gap between the end of the reed and the end of the mouthpiece to which it's attached. Now, this end of the thing is in the player's mouth, and he generates a pressure against this end, which is higher than any pressure inside the instrument. Now, the stream of air goes through that chink there and starts a vibration going. Now, once the vibration is going at the frequency of this tube now, as though it's closed at one end, the pressure that's generated at this end opens and closes the reed further. That is, when the pressure builds up, the reed opens further. When the pressure gets below the surrounding pressure, the reed closes. And when it's open, air flows into the system and helps to maintain the vibration. It's a little bit like somebody in a swing. You know, if they're swinging and you give them a push every time they get up to the end of the swing, you'll build up a large vibration amplitude in the swing. And that's basically the way this thing behaves. Now, again, you can effectively shorten the tube by opening holes along the length, and so this represents a side hole in the instrument. You open this key, the instrument is shortened by that amount, and so the frequency is lowered. Now, another thing is that, excuse me, I'm sorry, I want to say one more thing. Here is what's called a vent hole, and it's normally covered by another key which keeps it closed so it doesn't have any effect. However, remember that this tube that's closed, now I guess I didn't mention that the mathematicians and physicists have worked out that a tube closed at one end will vibrate with only the odd modes, 1, 3, 5, 7, and so on frequencies. And I'll show that in just a moment. But now, if we open a small hole in the side, we can kill the fundamental resonance. We can make it very difficult for that resonance to sound. Actually, put it way out of tune and give it a lot of losses, so it doesn't work. But if this hole is in the proper position, then the next mode can sound. And so by opening this, we can make the thing, opening this hole, we can make the thing jump from the lowest mode to the next mode. Now I guess I'm through with that slide. Now I have a piece of brass tube here, which I'll illustrate this. It will take a clarinet mouthpiece. Now, if I have some holes drilled on the side, which I want to cover up for the time being because I don't want them to be there. So when I sound this now, I'm sorry, it takes a little while to get my lips in shape to do this thing right, and the squeals you'll have to excuse, they don't belong there. Now there is the fundamental vibration frequency of this piece of tubing, and it has a fairly clarinetish sound, you'll notice. Not that one. I'm sorry, I must not, yeah, if I don't have my fingers on these holes properly, it's likely to squeal like that. All right, but now this thing, as I said, has modes of vibration, 1, 3, 5, 7 times the fundamental. So the next mode of vibration will be 3 times the frequency, and will be an octave and a fifth higher then. And there it is. I open a small hole here, and that kills the fundamental and allows the next mode to vibrate, and so there it is. Now, if I open a different hole, I can kill the first 2 modes and make the third vibrate. I have to do it in sequence, however, because it's a little bit cranky. Now you recognize the first 3 notes of that odd harmonic series that I showed you. So there are the first 4 tones of the tube with its closed at one end, and you see they fit pretty well that odd harmonic series. And so this is the way the clarinet presumably can vibrate. The 7th was a little bit flat. That has to do for reasons that I'm not going to go into. I'm not quite sure myself right now. But the thing will vibrate then in those modes. Well, we can build this into an instrument that we call a clarinet. And here it is. So it's basically a tube that's closed at both ends. You might notice here the length of the instrument, about like this, is about the same as the length of a flute. But any musician knows that this plays almost an octave lower than the flute. And the reason, of course, is that it's closed at one end and the flute is open at both ends, and so there's that octave difference again. So we build up the instrument, and if we forget about the rest of this for a moment, we have the same basic scale that I pointed out exists on the other instrument. It happens to be a minor scale, but that doesn't matter. It's still there. So we have this register. And there we have beginnings, at least, of a scale. The trouble is that in the next register, on the next mode, I guess I explained what I mean by a register. We play on the lowest mode, we're in one register. We play on the next mode, we're in the next register. And I've been using the terms interchangeably. So the next, starting out with this, now going up to the next register, you see I've got a big gap in there, because of the fact that this thing, the next mode, is an octave and a fifth higher. It's not like this flute. Where'd I put it? Well, anyhow, yeah, here it is. This one, I could cover the scale, and then the next register joined on right away and went up in the scale up an octave higher, and there was no problem. And the flute does just that. What we call overblowing. It overblows the octave, and so we have no problem. But the clarinet, we have this problem that it overblows an octave and a fifth. And so we have to fill it in somehow, and so that's the function of the rest of the instrument down here. We add on some notes at the bottom, and then we put on a few extra notes at the top. And by so doing, we can fill in the gap. So we start off here. And then we put a few notes at the top. And then we go back and use the whole instrument and open this vent hole and go into the next mode. And then we have a complete scale. It makes the clarinet a little more awkward to learn because it has these extra holes at both ends of the basic scale, but of course it's perfectly practicable. And we get up to this point, At this point, we're only using the instrument down to here, and we want to go higher than that. Then we have to get on the third mode of vibration, which is a sixth above the second mode. And this we do by opening extra holes, what's called cross fingerings or fork fingers, and I'm not going to go into that. But we can play up another octave in the clarinet. A good player, I won't try to get up there, but a good player can get up another octave above that note that I just played. Now, I might point out one reason I think that the bell of the instrument is of no great acoustical significance is this. If I put a cork in it, plays just the same as far as I can tell, except for the two lowest notes. You can't play the lowest note, of course, because you can't blow through the cork. That one won't play. And the next one is rather poor. But from there on up, see, that one is not very good, and this one doesn't exist. The lowest one doesn't exist at all. But from here on up, they sound pretty much the same. Well, that's enough for the clarinet for the time being. I have one more thing to say later on about it. Now, what we've been talking about so far are cylinders. Cylindrical tube for the clarinet, except for this end, which I don't think is important. But now there's another shape which has developed into a very important one musically, and that's the cone. Now, I have a cone-shaped tubing here. I have to apologize for my workmanship on this. I didn't mean it to sag like that. That's not a pertinent part of it. It's just that I found it rather difficult to wind up something into a cone-shaped tube. I finally did it by taking a piece of wood and laboriously planing it down into a cylindrical cone, and I wrapped glass wool around it and soaked it in boat resin, and came out with this, and I managed to get it off the
with a little coaxing, I can get the fundamental frequency out of the cone. Oh, it didn't take any coaxing at all. Wow.
Now there is the fundamental frequency of this air column. Now the mathematicians have worked out that a complete cone down to a tip has the same vibration frequencies as an air column open at both ends and of the same length. So obviously then an oboe and a flute, being roughly the same length, they're going to sound in about the same range. And furthermore, this will overblow the octave instead of the octave and a fifth. And this is of course what the oboe does. If I open up the vent hole in the right place, I will make it jump an octave. Another vent hole will make it jump up to the third harmonic. And if I go hard enough, blow hard enough, I can get up to the fourth harmonic. So there are the first four modes of vibration of a conical tube. Well, in the case of the oboe, all we have to do is put the basic scale on it again, and we have an instrument. Now, I didn't bring my oboe because it's not a very good one, and if I played it here, I think everybody would leave immediately. However, there is another instrument which I do play. This isn't mine, so I still have an alibi. If it doesn't sound good, it's because it isn't my own bassoon. I play bassoon. But this is a conical tube. It doesn't look like it at first, but it starts out as a cone, as a tube a little bit less than an eighth, a little bit more than an eighth of an inch in diameter here. It gets larger as it goes down through here, hits the bottom. Can I take this thing off? Where it goes around, is this gold plated or something? No, just brass. I don't know what to expect of Heckel bassoons, you see, with the price that they are now. They could be gold plated. Anyhow, the column goes down here, but this time it's the order of a little more than a half-inch diameter. Goes back up the other side. This is called the boot joint, and it actually has two holes down it, which communicate by means of this thing on the bottom, goes up here, and by the time it gets out here, you see it has a diameter of about 1.5 inches. And overall, it's about 8 feet long. And so it vibrates at a fairly low frequency. And if you extended this out till it came down to a point, it would go out here about another foot. But you chop it off here and you put the reed on. So now if you close all of the holes in the instrument, you blow the lowest note that the instrument is capable of without some, you can blow a lower note by a proper gimmick, which I mentioned this morning, but it isn't something that happens very often. Well, the basic scale in this instrument is, again, the 3 fingers in this hand and the 3 fingers in this hand. I may have to sit down there to see. My instrument has a neck strap, and there wasn't one with this, so I'm playing it under difficulties. I think I will sit down. I'm tired anyhow. So the basic scale is the 3 fingers in this hand, 3 fingers in this hand. And then we start over again and blow the next mode. Now we help it do that by opening a vent hole again, as I explained for the clarinet, and that's done for the first couple of notes by opening this one hole just a little bit. It's called half-holing, and it's one of the delights of bassoon playing, because if you don't do it just right, you can get some terrible squawks out of the instrument. But of course, this makes a rather limited scale, and so to make the instrument go down to a lower note, the lower frequency, this extra stuff is put on so that we can start out clear down here. And then by opening holes up the length of the instrument, we go up the scale. Now I'm up to the beginning of the basic scale here, starting with G. Now we start over again in the basic scale and up in the next mode. Now at this point we have to use subterfuges. We go into higher modes and we make them form by various and sundry forked fingerings, which is again another delight of bassoon playing. This is what a fellow working in the same field calls a fossil. It hasn't changed any in a couple of 100 years. This basic scale is the same as it was 200 years ago. And I hope someday that something can be done about that. But at any rate, we can go on up by the proper forcing it into other modes by various fingerings. In fact, bassoonists have, you might say, dictionaries of fingerings that they can refer to, and every instrument is likely to be somewhat unique in that respect. But we can go on up. Now that's as high as I know how to go on the instrument, but that will do. So it makes, actually it's a very nice toned instrument, in spite of its idiosyncrasies. Of course, as I pointed out, we have all this length on here to make it play down to this low B flat, what I would call B flat 1. It's the first B flat in the piano scale. Well, it's actually the second B flat in the piano scale. So by putting all the keys down, we get that note. Now, in order to get these higher notes, we have to, I pointed out in the case of the clarinet, we have a vent hole that we open to get the next register. Well, this actually has to have a series of vent holes, and we have a number of them up here. The left thumb has all this work to do. This is, again, one of the problems with the bassoon playing. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 keys for the left thumb to operate on this particular instrument, and so it keeps pretty busy. And every time somebody invents an improvement for the bassoon, the only thing they can do is to put on another key for the left thumb. So I hope there aren't too many more improvements made on the instrument. Well, this length, of course, out to here is strictly to give that lowest note. If I take this piece off, then I still have a perfectly playable instrument. It's a little awkward to hold without my neck strap. If we take this piece off, then we're beginning to be constricted a little bit. But it'll still play. I have to find the hole. I don't have anything to go by, you see, with my hands. Now, by the time we get down to this point, now we're getting quite restricted. We only have a few notes here. And of course, they don't sound very good. They don't have the rest of the instrument to help them out. If we take the crook by itself, now we're down to just one note. We have no flexibility whatever. Of course, the reed by itself also has a tone. We see now we're dealing with an air column just this long. Well, a few more things about the woodwinds. They have been developed over a period of a couple of hundred years, as I say, and actually pretty good considering the things that have to be done. One of the problems in playing woodwinds is this matter of reeds. You may have noticed on this instrument, here's a reed which looks rather different than the ordinary. This is a synthetic reed that I've developed and which I have high hopes for. I have some here that you can look at later on if you want to. I hope one of these days to make one of these for my bassoon and have a reed that will last forever and be reliable and not have to be played on for half an hour before it starts to behave itself. Another thing that's been of concern to woodwind players for years is the matter of what you should make them out of. Flutes are made out of metal, and however, this hasn't always been the case. Up until the turn of the century, flutes were made out of wood, and I've even been told that when metal flutes started coming out, that Mahler would not allow them in his orchestra. He thought they sounded like the very devil. But nowadays, metal flutes are not only accepted, but I've never seen a wooden one that anybody uses at all. And they're made out of various metals. A friend of mine has a gold flute, which he swears by, and naturally, because it cost him $1,200, and that was a long time ago. And it would be awfully strange if he didn't think it was the best sounding flute in the country. But I have looked into this matter of the effect of a material, and I side with the people who says it doesn't have any effect. That what you need is something which confines the air into a column that vibrates, and it doesn't matter what it is. I went through quite a series of tests on clarinets. I took this clarinet and arranged it to blow into a tube that would absorb all the sound coming out of it, and see how much sound is radiated by the body. And the amount radiated by the body is insignificant. And I finally dreamed up this thing as a demonstration. There's been a lot of argument among people as to the relative merits of metal and wood clarinets. Well, my assertion is that if there is a difference between a metal clarinet and a wood clarinet, there ought to be a big difference between a wood clarinet and this thing here, which is a piece of Tygon tubing, which I can stick a clarinet mouthpiece on, and I have some holes punched in the side. Now, I have fooled non-musicians with this thing, having listened to that clarinet and listened to this, and they have been fooled by which is which. Of course, it isn't meant to be an instrument that you would play in an orchestra. To get the next register, I have to open the vent hole by taking out that plug, and now it'll play in the higher register. And of course, it's hard to maintain a good firm embouchure because it wiggles so. And it's hard to keep your fingers over the holes in just the proper way. They're likely to leak. But it does, I think, illustrate my point that the material of a clarinet is not an important factor in its sound. It's kind of curious. This thing has been on television shows. I've been on Art Linkletter show one time. It just illustrates that nobody pays any attention to your serious work, but you come up with something silly like this, and you're famous at once. So, we do have woodwind instruments that are of quite high merit, and I hope that by learning more about them with the studies that I've been making, that we can have still better ones. And I hope that I can do something someday to the bassoon to make it a better instrument without some of the discrepancies. Oh, well, I forgot my other cone here. One of my attempts at making a cone was this paper deal. This is just wound up out of wrapping paper and then shellacked. Oh, isn't that a beautiful tone? As a matter of fact, this illustrates something which occurs in woodwinds, which people are beginning to look at now seriously. There is actually a book out. You can do certain odd fingerings on the woodwinds and get these tones. I don't quite understand it because they were the things that I was taught to avoid when I was learning to play an instrument. Now people are trying to use them seriously in music. There is a concerto for English horn, I understand, which uses these crazy fingerings to get these weird sounds. I don't know what the future of that sort of thing is going to be, but this illustrates one of those sounds very nicely. This is the kind of thing I get out of my bassoon when I don't mean to. It's very embarrassing when it doesn't belong there. Well, we have another class of wind instruments, and I'll say a little about those. I don't know where they began in history, but I have a sort of an idea. If you go down to Baja California on the west coast, go down below Ensenada about 20 miles and then go out to what's called Punta Banda, there is a little village called La Bufadora out on the ocean. And it's a place where the ocean comes into a cleft in the cliff and spouts up quite a tremendous height. It's a very spectacular thing, and lots of people go out there and look at it. And on the way out, there are the Mexican vendors selling their various and sundry things to eat and so on, which you shouldn't touch if you know what's good for you. But one of these stands has a lot of these shells on it. And the man there will sell you the shell, and you pick out the one you want, and he'll take a hammer and knock off the end. And when you do that, you have an air column. It's all curled up, but it's essentially a conical air column. You put your lips against it, and you get a beautiful sound. Now, people have known how to do this for centuries. And, of course, when you're coming to this place, you hear this sound because the fellow is demonstrating his shells, and you hear it from a long way off. But at least this is the beginning of an instrument that you can sound by using your lips as a reed, not a reed made out of cane or some other material, but your lips. Now, naturally, people would start experimenting with other things. You take a tube, for example, and put on the end. I'm just putting on something that I can blow on comfortably. My lips won't fit on this narrow tube very well, so I put this on for comfort. And again, let me say it will become apparent that I'm not a brass player, so let me get my apologies out of the way in advance. But this tube will blow. It will have modes of vibration, just like the others that we've been looking at. Now, which mode does that remind you of? It's not quite complete. I don't have the lowest mode there. But if you remember that series of odd harmonics, you'll recognize everything except the lowest one, and I can get the lowest one by putting this clarinet mouthpiece on it. So let's try it again there. So there is the fundamental of this particular piece of tubing. So now let's go through that series again. Here's the fundamental. Now I put the other thing back on, and I reverse it. Well, it doesn't matter. It works either way. It doesn't matter whether we use one end or the other. Now I think you recognize that odd mode series again. So this tube is vibrating as though it's closed at this end, which is natural because that's the way a vibrating reed end looks acoustically. It looks like a closed end. So this is not very useful musically. The gaps are too big and the notes aren't in the right places. However, over the centuries, instrument makers learned how to do something about this. To begin with, the sound that comes out isn't very good. It's not a very loud sound, but if we make the end a little larger, you see, immediately we're getting more sound out of it. So this is something to begin to do. We start flaring the end out, and when they started doing that, it became apparent that that also changed the tuning of these modes. And so we find then that if we flare the thing in the right way, which we do by, this is a trumpet bell, which I can fasten on with an adapter that I made specially for this lecture, as you can see. You see immediately that by shaping this thing, we have dragged those low frequency modes up until the thing is now approximately in tune. So there's the series of modes that we associate with a brass instrument. Now, they're not quite right yet. A good brass player will tell me, though, well, it's too sharp in the high register, so we do something more to it. We draw it down at this end, and then we put on a mouthpiece. Here's a mouthpiece, and this constricts. I don't have the leader pipe on here, so it isn't complete in that respect, but we do taper it down and then flare it out into this cup, and this has the property of pulling down the high modes a little bit. You won't hear it. I'm not that good a player. But we do end up, sorry, we do end up with the modes that you associate with the usual trumpet. However, there's one missing, this fundamental. We have pulled the second mode up to where it is now in a usable position. Where is the fundamental? Well, we can find that out by putting this clarinet mouthpiece back on. And there it is. It's way down there where it can't be used. So we actually use then only the second, third, fourth, fifth, and so on resonances. And of course we get a better sound out of it because it's flared out, and we get the more or less the present shape. Now all we have to do now from this point on is to fill in the modes, the space between the modes. Now between the first usable mode is actually the second mode of vibration, as I pointed out. Looking for my mouthpiece again. Now we have the space then. There are the two modes that are farthest apart. That's the second and third, and we have to fill in that space. Now there are various ways of doing, a couple of ways of doing that. One way is one you're all familiar with, the trombone. Simply does this. I don't even know how to hold a trombone, to be honest with you, but how does any brass players here? I'm not a trombone player either, am I? So let's see something. Oh yes, there's a release here. Yeah, here we go. So we can lengthen the tube by stretching this thing out, and all you need are 6 additional notes here, 6 additional positions, a total of 7 positions to fill in the space between the C on the staff and then the next note above, the G. There's an 8th position when you pull this thing all the way off. I won't illustrate that one. It's not looked on with favor. So this is a long-standing and honorable way of filling in the space between the modes by simply lengthening the instrument, and it's a good one because there are no problems associated with it acoustically. All the problems are in putting the slide in the right place. Now the other alternative is the trumpet. We've wound it up, of course, into a closed loop here in order to let's see, I don't know where I put them out. Here it is. We wound it up into this closed loop. It's rather awkward to use when it's stretched out like that, although I've seen one at Idlewild which was 12 feet long, blown to announce supper. Now what we can do here to fill in those 2 modes is to use the keys here, which do the following. When I push down the middle valve, when I don't have any valves pushed down, the sound goes right straight through this whole system. Comes in, goes around, goes all the way through, and comes out. So the tubing is essentially just this length. Now if I push down the middle valve, I make the sound go through this little bit of tubing here on the side. So that makes it longer. And this tubing is adjusted to make it go down a semitone. Then similarly, we put the first valve, enough tubing, a little more this time, to make the thing go down a whole tone. And then by using the 2 valves together, we can make it go down a minor third. And similarly with the next valve, we can use the second and third, first, third, and then all 3 valves down. And so we have the 6 additional notes that we need to fill in that space. There is one difficulty with this. There are certain discrepancies involved here. If I want the frequency to go down corresponding to a semitone, I have to increase the length by 6% very nearly. So you push this down, you increase the length by 6%. Push this one down then, that's 2 semitones. You want to increase the length by 12%. Well, when you have this one down and then push this one down, you want to increase the length by 6% of the new length, not the old one. And the two together don't come out to be quite right because of that reason. This is 6%, say, of the original length. Now, when you've pushed this down, you want this to give 6% of the new length. And you can't satisfy both of those, not with this simple valve mechanism. And so there are discrepancies that have to be allowed for. Fortunately, the trumpet player is in the position of being able to change the frequency a little bit by his lips. So he can accomplish that. And trumpets nowadays, I see this one has. I have an old trumpet that I bought for $10, which I use for my experiments because it doesn't matter if I damage it. Now this one has a slider here. You can for some notes. See, I guess this. I'm not quite sure how this one works, but it is possible to use your little finger to extend this slide and to compensate for those discrepancies, at least to some extent. The larger instruments, you'll notice tubas lots of times have 4 valves on them for that reason too. It allows compensation for some of these discrepancies. Well, what I've tried to show here is where our instruments come from, that you can start out with simple systems and end up with musical systems that are really quite satisfactory. In fact, you can make music out of a lot of things, even a bundle of sticks. Here's a bundle of sticks. Now you see there is a system that you can do something with too if you want to. In fact, if I want to, let's see, if I want to arrange these. So there, with that little tune, I will end. So that's all the formal presentation. Thank you.
John Backup has indicated to me he'd be delighted to ask a question.
Yes.
You have an instrument that has both ends open, like the
Recorder. Yeah.
I would think that if you want to go an octave above, that you would have the hole that gives you the next octave halfway around the instrument. Is that
Well,
the way? Because you'd want to relieve the high pressure area at the center, right?
yes. Well, I'm really not sure. I'm not sure where there is a vent hole in the flute. Well, I'm not sure about that. As I say, I had a summer session in Woodwinds once, and I played the flute for I think all of a week, and I could never get down to the bottom note. I believe the flute player pretty much can control by the way he blows the airstream. He doesn't need a vent hole necessarily. He can make it jump the octave without that. But any flute players here? Yes.
No, there's no vent hole.
Yeah, well, that's, I hadn't heard of one. I haven't really, see, the flute is a completely different system than the ones that I've been investigating, and so I have made no experiments on flutes at all.
See, where's the vent hole to get an octave in the instrument that is closed one in like the clarinet?
Yeah, well, in the clarinet, here it is, right here. This little one right here. You push this down with your thumb, and that opens this hole.
It's hard for me to see how that suppresses the fundamental. It's just not ringing.
Well, it essentially opens a big leak here, but this happens to be at the pressure node for the next mode, and so it doesn't affect the next mode, and so that one can vibrate freely. But the lowest one can't because this is getting to a higher pressure.
It's a node for the next mode.
Yes. Yeah.
Yeah, it's got to be.
Uh-huh.
Well, what's the difference in those two cones? One that's well behaved and one that's...
I think the difference is that this doesn't come down quite narrow enough. I think what is happening here is that this, because it actually is a cone that should be about this much longer before it comes to an end, it's been chopped off short, and this distorts the modes. So I think that the next mode is more than an octave above the fundamental, and what it's doing, I think, is oscillating between those two modes in some fashion.
They both fit your oboe reed, though, but this bore is larger, is it?
Yeah, this is a larger bore. I just made this freehand by taking paper and rolling it down as tight as I could. And this was the best I could do to get it this narrow, and it should be narrower. whereas this one was made on a form, and it looks the same width, but actually this is a lot thicker, so this is a finer bore inside.
Is there a theorem about trumpet sound to the outside world by using an exponential horn like that on a trumpet? Is that the reason it sounds better?
I don't know for sure. This is not an exponential horn. No, it's a long ways from it. You plot out the shape of that, and it's nowhere near an exponential horn. The shape has to be the one which will push those modes in the right places, you see. Drag those low modes up and put them where they belong. And that is a critical function of the shape, but it's not an exponential. It's strictly an empirical one, as far as I know. It does radiate better at the higher frequencies because of this, and that's one reason why it sounds louder. The high frequencies radiate better than low ones. In fact, the reason that it doesn't have any higher resonances, those that saw the colloquium this afternoon, I had the trumpet resonance curves. They disappear at the high frequency end because there's no reflection of the wave at this end. It all goes out and radiates out. In a tube like this, practically all the wave that hits the end is reflected back again, even though it's open. As I pointed out, in a thing like a clarinet, the sound is actually coming out the holes in the side, and of the energy that you put into sounding the clarinet, only about 1 to 2% of it comes out as sound energy, so they're very inefficient things. This is characteristic of musical instruments.
In the trumpet, which is closed at one end, the long one,
Yeah.
you mentioned that the modes that you got were the odd number.
Yes.
But then when you made it more to the trumpet, you got most of the modes. I think I missed the transition from the odd.
I forgot to show the last slide on the series there. This, I think, will appeal to musicians more because it shows what's going on here. I sort of forgot about this one. But this shows the transition from the straight tube into a trumpet. First, yes, here we are. Okay, can you raise it a little bit? Now we start out with a tube. Now here we have the fundamental. This is on a musical staff. It's somewhat distorted because these represent semitones. Each small line represents a semitone, and of course from here to here you've got 4 semitones. From G to this is written wrong here. This should be A, but rather B. From G to B you've got wait a minute. What am I thinking of here? Something is labeled wrong on the side. But you have 4 semitones between some and 3 in others. But starting out with this as the fundamental, then here is the octave and a fifth above. This is the 3 times the frequency of this. Here's 5 times, 7 times, 9 times, 11 times, and so on. So here is the odd series of harmonics. That's just the straight tubing with nothing on it. All right, now if we put the mouthpiece on and don't do anything else, we have to alter the length a little bit, of course. We can keep the fundamental in the same frequency. All these lower ones stay where they are, but the upper ones are all pulled down. Now this is the reverse order that I talked about just now, but we put the mouthpiece on and we pull these higher ones down to where they are here. Now we put the trumpet shape on the thing. Now we leave the high ones where they are and pull the low ones up. Now you see this one has moved up here. Now we're down to the series that sounds like the regular harmonic series, where this is 2, 3, 4, 5. 1 should be down there. It should be an octave below this one, but it isn't. It's actually way down here. That's. Did I illustrate that? I think I missed that. This is something that I wanted to show. You see that I showed the lowest mode, the lowest playable mode in the trumpet. Now that is this one that's the